Welcome. In this section, we'll implement the all-pass filter in Python. So I have imported some libraries here, NumPy and matplotlib. And essentially what we are going to implement is this equation, which we derived in the last section, where yn is the output, xn is the input, xn minus 1 is the delayed version of input, and yn minus 1 is the delayed version of the output. They are being multiplied by a coefficient called a. So let's get started. So let's say our sampling frequency is fs. Let me just zoom in. fs, and it is 44100 hertz. Then let's say I want to simulate this signal for a duration of 100 milliseconds. So duration is 0.1 second. So total number of samples in this duration will be integer value of duration multiplied by the sampling frequency. So now I'll generate my time axis. This is my start point, which is 0. It is going up to the duration of the signal, and the number of samples is is n, and endpoint is false. Okay, so this is what is my time axis, and I will generate a signal with a frequency. Let's call it frequency 1. Let's say it's 1000 hertz, and I'm going to generate a sine signal. So let's call it x. This is going to be the input to the filter. So x here is a sine wave, and that is 2 into pi multiplied by frequency multiplied by time. So let me just quickly plot this. So I have time versus my input signal. Let's see if it's fine. Oh, frequency is not, frequency 1. I have to write frequency 1 here. Okay, so yeah, let's just adjust this figure slightly. Let's make it 15 by 4. Okay, so so you can see that my sine wave, that is x, that is input to the filter, is generated here. I can actually zoom in slightly. Okay, so you can see this is the sine at 1000 hertz with amplitude of plus and minus 1. Now this becomes my input to the filter. Also, at this stage, I would like to see the spectra of this input signal, which should be a line spectra at 1 kilohertz. So for the time being, I'll just disable plotting, and let's see if I have to calculate FFT. So FFT can be calculated. Basically, I want to know the spectra of the input signal. So this can be created by taking the FFT of the input, and this will give a complex number series. I only want the magnitude of it, so I'm going to take the absolute of this. So this is as far as input FFT is concerned. I also need, for the spectrum, I need frequency axis. So for generating the frequency axis for the spectra plot, I will do this. So basically, my FFT frequency is my total length of the input, and I have to specify the sample time. So my sample time is nothing but inverse of my sampling frequency. So this will generate the frequency axis for the spectrum, and I can do a very rough plotting to see whether this is working or not. So I'll this is my frequency axis, and I want to plot FFTX against it, and let's see what we get. So we get a we get a spectrum, and both complex and imaginary as well as real spectrum of the signal is appearing here at 1 kilohertz. So let me just refine this. We don't need the imaginary spectrum. So what I'm going to do is that I'm going to refine this figure. So let's firstly copy this and get it here. Define the figure size. And what I can do is I can define, I just want to define the size of the FFT that I want to plot. So I will take a slice of it. Let's say X slice, and slice is nothing. I want to just keep the real part of the FFT. So from zero to the Nyquist frequency. That means I just want to go up to half of this in the positive direction. So once I have defined this slice, then I can just mention it here like this. X slice, and here also X slice. And let's see, let's run the code again. There we are. So now you can see the imaginary part of the plot has gone, only the real part has remained, and this is at 1 kilohertz. In fact, we can further refine So now I just want to see the spectra only from 0 to 5 kilohertz, and I want minor tick marks to appear here so that my spectrum becomes more clear. So for that, I will limit the spectrum to, say, 0 to 5000, that is 5 kilohertz, and I want my tick marks to change, X tick marks, so I will specify them from 0, I'll specify a range starting from 0 going up to 5 kilohertz in steps of 250 kilohertz. So let me just run this code now. Wonderful. So as you can see that my x-axis has changed, it has become more zoomed in, and I have a line spectra at 1 kilohertz because our frequency is 1 kilohertz. So as of now, we have just analyzed the input to the filter. So now let's start building this filter one by one. So currently I don't need to see this plot. I'll disable it, and so let's make the all pass filter. Okay, so first I have to define a placeholder where I'm going to store my output of the filter. Output of the filter is y, so I'm going to initialize an array which is as big as the input, that is x. So this is where I'm going to store the output of the filter. So now what I'm supposed to do is that I'm going to take loop through each and every input sample, that is for n in range the entire length of my input. That means looping through each samples in the input, the range, let me correct, yeah, this is range. So basically what I'm doing is I'm implementing this equation right now. So what it says is that I have not actually initialized a also. So a is the coefficient of the filter. Let's say a is equal to, it has to be less than 1. So let's say it's 0.1. So what I'm going to do right now is I'm going to store the output by implementing this equation. So the first term is a multiplied by x and the current sample. And these samples will start from 1 and will go to the entire length of the input. So basically I've implemented this term. Now I'll implement this term, which is nothing but n minus 1. And then I have to implement this term, which is minus a y n minus 1, which is quite straightforward. So this is going to be minus a into y n minus 1. That's it. This is just one line code. This is what is all pass filter, and that's all that we are required to do. So what I'm going to do is the way I calculated FFT for the input, I will also calculate the FFT for my output. So I'm just going to take this and modify this. This is y and this is y. So this is the spectra. This is how I'm going to calculate the spectra for the output of the filter. And okay, so let me also then plot this in this plot. And so I'm going to repeat this line of code, but this time for the output. So I'm going to change frequency x is going to remain the same, slice size is going to remain the same. All that is changing is this. This is the FFT for y. And okay, let's put some labels also. So this is input spectra. This is output spectra. And I'm going to enable the legends so that we can see it in the plot. And yeah, I will enable this plot. Let's see. So let me just run the code. And as you can see, both input and output spectra are aligning, which means the filter has allowed 1 kilohertz signal to be passed through it without getting attenuated or without generating any degradation or harmonics. They are overlapping. So let me just correct that overlapping part. Let me make the input spectra slightly thick so you can see it in the background. Let's plot it in blue color. Line width is what I'm going to change. So line width is, let's say, 5, and let's say this line style is dashed lines. Okay. So now you can clearly see. You can see that both orange and blue lines are overlapping with each other. There's a line spectra for both output and input centered at 1 kilohertz. Which means now, irrespective of what frequency you set here, this filter is going to pass it. We can play around with it. For example, we can change this to 2 kilohertz. And you'll see that my frequency of both input and output has shifted to 2 kilohertz. We can shift it to 3 kilohertz. And it has shifted to 3 without any attenuation. The signal part is remaining the same for both input and output, which means the filter's transfer function has a magnitude of 1. It is allowing all frequencies to pass through it, which is what is the characteristic of the all pass filter. We can say we can pass 4 kilohertz and it will again go through. So here is 4 kilohertz. So no problem. As far as the frequency is concerned, the filter is allowing all frequencies to pass through it. We can also then plot these in time domain, the way I did it earlier. So let me just remove it from here and do a time plot of y. So I'm just going to copy this code, and now I'm going to plot y, which is the output of the filter. And let's see, we'll build this up. So here we are, wonderful. So as you can see, both, okay, I'll label them so that you can clear it. You can clearly see it. Let's say label, okay, filter input, and let this be filter output. And I'm going to enable the legends. And I'm going to reduce the time here, reduce the x-axis basically. So here you are. You can clearly see that both my input and output are swinging to 1, +1 and -1. So the signal is not getting attenuated when it is passed through the filter. But what we can see is that there's a phase difference between the blue and the orange line. They're not overlapping anymore. And that's exactly is the definition of all pass filter. It manipulates the phases. It does not change the magnitude of the signal. So based on the frequency that we are passing through this filter, this phase is going to change. Also, how fast this phase is going to change is dependent on this coefficient. Let's say this was 1000 hertz. We can try some other frequency. Oh, this was 4000 hertz, sorry. Let's say we can try 1000 hertz. And again, you see that as far as the amplitude of the input and output are concerned, they are still swinging between plus and -1, which means the filter is not attenuating the signal based on the frequency. But you can clearly see that there's a gap between input and output, and that gap has come because of the phase that has been, or the delay that has been introduced by the filter, which is leading to phase difference between both the signals. And this is dependent on the frequency. It will change. For example, if I take now, say, 3 kilohertz, the phase will be different. This is 3 kilohertz, and the phase has shifted here. Also, it also depends on the coefficient. So closer it is to 1, the signals will start overlapping with each other. So let's say it's 0.9, and you see that the signals, the phase difference between the signals have almost reduced to 0. And that's how you're going to manipulate the phases of the incoming signal. As far as frequency spectrum is concerned, you can see that both the spectrums are overlapping, so there's no problem at all. As far as amplitude of the signal is concerned in time domain, they are just the same, no attenuation. The only thing that we are changing is the phase of the signal, and that's exactly what all pass filter does. And this is what we are going to use in our phasers and flangers and chorus. Hope you enjoyed this session. See you in the next one.